Hello everyone. In this video, let's learn about flip-flops with additional inputs. So the flip-flops we've been introduced to in the previous lectures, they have like D input, common clock input, and they have a Q state output and a Q prime. So some flip-flops have additional inputs which can be used to set the flip-flop to an initial state independent of the clock. So as we see below here, this flip-flop, D flip-flop has a clear N and a preset N inputs. So the small circle, the bubble here, or the inverter, it indicates that a logic 0 rather than 1 is required to clear or set the flip-flop. In other words, this type of input often referred to as active low, which means a low voltage or logic 0 will activate or enable the clear and the preset inputs. So when 0 is applied to the clear N, this will reset Q to 0. And then when 0 is applied to the preset input, this will set the flip-flop to Q equal 1. So let's summarize this flip-flop operation in a table. And as we see on this clock symbol here, this is a rising edge flip-flop. So we have the clock input, we have the D input, and then we have the preset, and then we have the clear input. And then we want to figure out what will be the next state. So for preset 0 and clear 0, 0, and remember 0 means this will activate the pin rather than 1. So this will be, we don't care about the D input, we don't care about the clock, this is not allowed. Similarly to the set reset flip-flop, we said we cannot enable both pins. So let's see when preset is 0 and clear is 1. So as we said, preset is 0 will set the next state Q to 1. So that means the Q plus will be 1 regardless of the D input and the clock. How about when a preset is 1 and the clear N is 0? So in this case, clear N is active and preset is inactive. So when clear input is active, this will set the flip-flop to Q equals 0. So that means the next state will be 0. We don't care about the D input. We don't care about the clock. How about when preset is 1 and the clear is 1? So that means both of them are inactive. So in this case, this will be the normal D flip-flop operation. So which means, because this is a rising edge flip-flop, on the rising edge, if the input is 0, the next state will be 0. And then if D input is 1, and then we have rising edge, and the preset is 1 and the clear is 1, so that means the next state will be equal to 1, same as D input. Last situation, when a clock is 0, 1, or we have falling edge, so we don't care about the D input when a preset is 1 and a clear is 1, so we will always hold the previous state. So this will give us Q or no change in the state. So to better understand this, let's do this timing chart. So let's try to figure out how Q will change. So let's assume the initial state of the system is 0. So Q is 0. This is a Q. So let's look on this rising edge what's happening. So we have the D input is 1. However, clear N is active. And clear N will set the next state to 0. When clear N is active, the next state will be 0. So that means Q will remain 0. So Q will remain 0 until the next clock edge. So let's look at this rising clock edge, what's happening. So D is 1, a clear N is 1, which means it's disabled, and a preset is 1, which means it's disabled because these are active low. So that means the next state will go to 1, will be the same as D. So this will go to 1 until the next rising edge. So now we have rising edge, so let's see what's going on. So now D is 0, clear N is 1, and the preset is 1. So that means the clear N is 1 and preset is 1. We have normal D flip-flop operation. So that means the Q will be equal to D. D is 0, so the next state will go to 0. So let's be careful here. Here we have a preset is going to 0. So when preset is going to 0, that means it's enabled. So if preset is 0, the next state will be 1. So that means the Q will go to 1 here. Until the next rising edge. So on this rising edge, let's see what's going on. So preset is disabled, ClrN is disabled, and we have 0D input. So that means Q plus will go to 0. So next, let's see some additional inputs for the flip-flops. In some situations, we want flip-flops to hold existing data, even though the data input of the flip-flops may be changing. And this is the case in registers. So what do we do in this case? One way to do this is to gate the clock. So let's draw D flip-flop. So we have D input, we have the clock, let's assume falling edge clock, and then we have the Q output. So one way to do this is to gate the clock using AND gate. So this will be the clock input, and then this will be the enable input. So when enable is 0, so the clock is disabled because the output here is 0. When enable is 1, so that means the clock is enabled. However, this method has two potential problems. The first problem, so we know there are delays in gates. So gate delay may cause the clock to arrive at some flip-flop at different times than other flip-flops, resulting in loss of synchronization. The second problem is that if enable changes at the wrong time, the flip-flop may trigger due to the change in enable instead of due to the change on the clock. So again, this will result in loss of synchronization. So rather than gating the clock, we can use D flip-flops with the clock enable input. So let's see how we can do this. So the clock enable input can be represented by CE, clock enable. So let's see the symbol for it. So this flip-flop has D input, has a clock enable, CE, and has the clock, normal clock signal. So the bubble means falling edge. So this is the clock input. And then on the output, normally we have a Q and a Q prime. So this is a Q. So how can we implement this clock enable in a different way than using an AND gate? So let's see the implementation. So this will be the clock input, and then we have a Q output. So simply we can use 2x1 mux. So this is a mux, and then this is D input, and then the control input is the clock enable. So this is CE, and then we have DN, data in, this is logic 1, and then we can feed back the Q, so which is 0. So let's see the characteristic equation. So Q plus will be equal to Q multiplied by CE prime or CE bar plus DN multiplied by CE. So let's look at this characteristic equation. When CE is disabled, so when CE equals 0, so that means we will get rid of this term here, and then CE bar will be equal to 1. So that means Q plus is equal to Q. We will hold the previous state. How about when CE is enabled? So when CE is enabled, so CE bar is equal 0, so we will get rid of this term here, and then we will be left with DN. So that means the Q plus, the next state will be equal to DN. So whatever we feed in DN, so Q plus will be equal to D equal to DN. So when using D flip-flops with the clock enabled to control the clock, this will resolve the synchronization problem. So this is all about flip-flops with additional inputs. I hope this was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.